All right, so hello everyone. Welcome to Recitation 11 on Mechanics and Materials 1. As always, we have 4 exercises today. The first 3 are the key exercises. So this is the first one. You are given a beam shown in the picture here, and you are asked to draw the moment and shear diagram for this structure. All right, so as we always do, we need to start with the free body diagram, and we need to calculate the reactions at the supports. So here we would have, let's say, a reaction at A. Let's call it FA. And then we have a similar one at B, assuming they are both upwards, which makes sense because the external force is downwards. We will have FA and FB upwards. And the next thing you need to do is to replace the distributed loads by singular loads. And you can do this as long as you want to compute the external reactions, okay? So when you need to draw the diagrams for shear and moment, this is obviously not the way to go. You need to look at the distribution. But if for this step, because you just want to calculate FA and FB, you replace these by concentrated forces. Okay, so each of them would be the area of that triangle, that is 1/2 times 4.5 times 5, which is 11.25 kilonewton. Okay, so these two concentrated forces that are supposed to replace the distributed forces, the triangles, they are 11.25 kilonewton downwards each. Also, their distance is, let's say, 3 here, 1.5, so 2/3, 1/3 for each of the triangles, obviously. Okay, now, if you look at this system, it's easy. You basically have 2 unknowns. You need to write 2 equations to compute those. And those equations could be equilibrium of forces and equilibrium of moments. For the forces, this would be, let's say, equilibrium of forces in the y direction. Assuming upwards is positive, this would be FA plus FB minus, let's say, 2 times 11.25 is 0. Okay, so that's your first equation. The second equation is equilibrium of moments with respect to a point, let's say point A here. And then if you do that from this moment, and from this force and this force, you get moments that are clockwise. From this one, you get a counterclockwise moment. So this would be a plus, these two would be minus. So if you do that, you get, let's say, minus 11.25 times 3 minus 11.25 times 7.5. Okay, so this is the first one, and this is the second one. And then the last one from FB, you get a counterclockwise, so it comes with a plus times 9. Distance is 9 meters. So this would be your second equation. So now you have 2 equations, 2 unknowns. You can compute FA and FB. If you do that, FA would be 9.375 kilonewton. FB would be 13.125 kilonewton. All right, so that's that. Now we have the reactions. What we need to do is to basically zoom into this picture, let's say like this, and cut it somewhere here, and find out what is the reaction there in that particular cross-section. So if you assume this is your, let's say, piece at distance x, you would have a shear force and you would have an internal moment. Okay? So we want those with respect to, let's say, FA and distributed load. So that's what we are going to do. We basically draw that little sample. So let's say you have something like this. At A, you have FA, which I would just, let's say, conveniently replace it with 9.375. Okay? Then you would have your distributed load. And here, again, there would be an internal force or shear. There would be an internal moment M. And now basically we need to repeat the same procedure for this, assuming that this is, let's say, our free body diagram, okay? So this is our free body diagram for the first part. After we do it for the first part from here to here, we do it then separately for the second part from here to here, okay? So for now, we are looking into this. That's why we have only one of these triangles. Sometimes, later it would look like this, of course. But first, let's look into the first part. Okay, so if you assume this distance is x, the force that you have here, it would be 5 divided by 4.5 times x, right? Because, sorry. 5 divided by 4.5 is the slope of the line. So you multiply by that x, and you get this, okay? So if you wanted to replace this distributed force with a single force here, then that single force would be the area of this triangle, and that would be 1/2 times x times 5 divided by 4.5x. Okay, so this is 5/9 x squared. Okay, so that would be the concentrated load in that place. So you use that in order to write your equilibrium of forces and moments. So what we want to do now is to think of this, let's say, this replaced system. So you can think, okay, this is your system now. You have 9.375 here, Vm, and you have this single force of 5/9 x squared, and the distance here is just x. Okay, so if you do that again for this system, for this simplified system, you write also equilibrium of forces in the y direction. Again, assuming upward is positive, and then you write equilibrium of moments with respect to, let's say, point A equals 0. And if you do that, let's say here you get 9.375. It's upwards minus 5/9 x squared minus v is 0. And then for m, you would basically get, let's say, m plus 5/9 x squared times this distance, which is x/3.
Is it 5/9 distance or 1/80? Can you check it? The orange equation, the first orange equation.
Okay, so this It's coming from this, right?
Yes.
So 5 times x divided by 2 times 4.5. It's 5 over 9x squared. Is that all right?
I thought it was 45.
Okay. So the next one here, we write the moment. That's the moment due to, internal moment. This is the moment of the force. That's the force times distance. And then you would have the moment due to that force 9.375 times distance x is 0. Okay, so these two equations, basically, they give you your equations for V and the equation for M. And once you have those equations, obviously you can also draw them. Okay, so you can draw your diagrams. And more importantly, you can also see where these things are 0, or if they are ever 0. Where is M0? Where is V0 if they are 0? Because you remember maybe that, the derivative of M is V, right? So if V is somewhere 0, it tells you M is reaching its minimum or maximum. So maybe you want to use that information when you draw your graphs. All right, anyway, if you do this, let's say for clarity, let me just write this. Vx would be 9.375 minus 5 over 9x squared. So this is the function for Vx. And then the function for Mx is 9.375x minus 5 divided by 27x cubed, which you can immediately see it's the integral of V. Usually you have a constant here, but because here M is 0, that constant is basically 0 at x equals 0. So that doesn't enter the calculations. All right, so you have your relationships for V and M, and once you have this, you can now use this information to draw them. But I don't want to do that. I want to go now for the second part and draw, calculate what happens in the second part of the beam. So we learned what happened here. We do this, and then we draw them all together. All right? So this was, let's say, the solution for the first part. In order to go to the second part, I will just duplicate this page and clean it up a little. Okay, so, sorry, we have come this far. Okay, this is for the first part of the problem. Now let's repeat the same thing for the second part. So what we want to do now is to repeat the same procedure, but what we will do is to cut it somewhere here. Okay, so if you cut it somewhere here, then this would be your beam. Okay, now for this one, you can use the concentrated replacement for the first distribution, because this won't change after this point, right? That is just a constant thing. And then for this little part, though, we repeat exactly what we did for this little triangle. Okay, but except that now our x-coordinate should be starting from here. So it would look slightly different, but in nature, it's exactly the same thing. So let's say we draw it like that. So you have 9.375. I use this concentrated force instead of the distributed force. And okay, so we assume this comes up to here. we have 11.25 kilonewton downwards here. And then, again, this is the x coordinate as before. And this is 4.5 meters. Okay, so from here on, we have again the same situation as we had previously. And we are looking for V and M again. Okay, so we will write our equilibrium of forces and moments. Again, let's say if you write equilibrium of forces in the y direction, assuming upward is positive, and we learned how to handle, this relationship. This was 5 over, previously here, this was 5 over 9x squared, right? So now this would be 5 over 9x minus 4.5 squared, because it would just scale with this length, which is x minus 4.5. All right? So that's basically the trick. So here, this would be 5 over 9, x minus 4.5 squared. And now that you want to write the equilibrium of forces, you would have 9.375 upwards, 11.25 downwards, 5 over 9, x minus 4.5 squared, and minus v, of course, equals 0. Okay? So this immediately tells you that v is minus 5 over 9 x minus 4.5 squared minus minus 11. It doesn't matter. 11 to 5 plus 9.375. Okay, for clarity, I just keep it like this. I don't simplify it. But you can, of course, simplify this too. All right, so this is your V. And of course, you can calculate M similarly as before too. So you can also do mx. And in order to do that, you would also write your equilibrium of moments. Again, let's say with respect to point A to be 0. And if you look at this now, again, you would have something like, let me just clean it like that. It would be something like m plus that 5 over 9 x minus 4.5 squared times distance here. Okay, so that would be 1/3 of distance, right? So you would have 1/3 of x minus 4.5. And then you would have the distance from this one. So this would be now 1.5 plus x minus 4.5, okay? So that would be the distance of that point 11.5. So that would be plus 11.25 times that distance. The distance, again, is, for clarity, I write it like this, is x minus 4.5, which is this distance plus this distance, which was 1.5 anyway. And then eventually you have the moment from just 9.375 times x is 0. All right? So you do this, and then again, you can simplify this. to get your moment equation, but you can clearly see your moment equation is a cubic equation. So after having all these, we can now plot them. So in order to plot them, again, you start from let me clean this picture a little here so that we can plot them on top of one another. So let's say this would be your shear force distribution. Underneath, we can also plot the moment distribution. And assume that this is 0.9. This is shear force, this is moment. Now, your shear force starts from 9.375. So it's somewhere here. You see, this is basically just this number, and it is upward, so it's a plus value. And then from your previous equations here, if you set this to 0, okay, so if you set this to 0, you find x to be 4.108. That tells you that's the point that your shear force is 0 or your moment is maximum. And you also see it's a quadratic function, it comes downwards. So you basically have a function which looks like this. This is where v is 0 and x is 4.108. And let's say it comes up to here where x is 4.5. Okay? And after that, basically the same thing repeats because you have a very similar quadratic function. So you would have something like this. Okay, this is not up to scale, but you get the idea. And also, at the end of this, you expect to end at, let's say, minus 13.125, because that was the reaction of your right support. Okay? All right. Also here, you know, in that moment, your shear force should be, in that x equals 4.5, your shear force should be minus 1.875, which you can compute it from either of these equations. Okay, so that's that. Now you want to draw your moment diagram. You can see moment starts from 0, and then it's a cubic equation. So if you plot it, and also you know that it's gonna be 0 here. Okay, so your moment would look like this. So this is the maximum. Then, because v is negative, your moment would also be negative. So, sorry, your moment is still positive, but you know its derivative would be negative. So in this little part, it starts coming down like that. Okay, that's an exaggeration. And then, okay, it continues like that up until it comes to 9. Okay, so you get the idea, I guess. All right. So this is how it is, and then the maximum. You can also calculate the maximum moment if you want it. All right. Do you have any question? And I think, if I'm not mistaken, this should be 25.7. You can check it from your calculation. All right, so this was the first assignment. It's a very nice exercise, nothing particularly complicated, but I think this sort of stepwise way of doing it, it's very nice for learning outcomes. All right, so the second exercise is the following. Now, you want to calculate the smallest allowable diameter of the shaft, which is subjected to the concentrated forces. So, and you have a journal bearing at A and a truss bearing at B, and your allowable stress is sigma 150 megapascal. Okay, so in order to do this, we use our formula, sigma equals MC over I, or sigma max is equal M max times C divided by I. I is your moment of inertia, so that would be pi over 4 C to the power 4. C itself is the diameter divided by 2, so that I is pi over 64 d to the power 4. Okay? So I is, a function of d. D is the unknown, right? C here is also d over 2. So that's also a function of d. And sigma max is given 150 megapascal. What we need to do is to find out what is the maximum moment, and then we will be basically able to calculate the minimum diameter, okay? So how do we find the maximum moment? If you just look at it, it's not so easy to, to identify that point. What we need to do is to draw the moment diagram, or the shear and moment diagram, like we did for the previous example. And if you have the shear and moment diagram, then you can identify the point at which you have the maximum moment, okay? So in order to do that, you need to compute the reactions at the supports. So here, let's say at A and B, we get our forces, let's call them AY and BY. And now for this picture, you have two unknowns. We write our two equations and we calculate the force, right, we calculate AY and BY, and from them we draw the shear diagram. From shear diagram, we draw the moment diagram. That's the idea. Okay, so equilibrium of forces in Y direction is our first equation. That gives you AY plus BY minus 12 minus 20 is 0. Equilibrium of moments with respect to, any point. Let's say A. Again, assuming counterclockwise is 0. So you have your 12 downwards multiplied by 0.5. So that gives you counterclockwise. This one gives you clockwise. So this is a minus. This one gives you counterclockwise. So it's a plus. Okay, so you would have 12 times 0.5 with a plus minus 20 times 0.4 plus 1 times by is 0. And from these two equations, you can calculate your two unknowns. AY will be 30 kilonewton, and BY would be only 2 kilonewton. Okay? So now that you have these reactions, you have a very simple problem to draw the shear force diagram. all you need to do is to basically cut it here, here, and here, and compute the shear force for each of these parts, okay? So if you cut it here, it's immediately clear that it is minus 12. You see, you have 12 downwards, so it would be minus 12. AY was 30 upwards, so if you cut it here, this would be plus 18. And if you cut it here, it would be minus 2, okay? So we can now do the same thing. We want to draw those shear and moment diagrams. Okay, so let's say this is the shear diagram. And I will just duplicate it to draw the moment diagram. So this would be shear diagram, moment diagram. Again, the shear diagram starts from minus 12. So it would be minus 12, then you have 30 upwards. You go all the way to something like 18. And then it would be 18 up to the point that you have the next force that is 20 downwards. And then in the last part, it's simply minus 2, okay? All right, so this is your shear force diagram, and this is minus 2. Now, for this, you want to draw the moment diagram. You can see moment is 0 here, starting at 0. And remember, again, M prime is V, okay? So here, when V is minus 12, that means you would have a line with the slope minus 12 in that range, okay? And also, if you remember the dimensions from the picture, you attach that picture to this. So this distance here is 0.5. This is 0.4. And this one is 0.6. Okay? So you will have a line with the slope of minus 12 coming all the way to this point that is at 0.5. So this would be basically your line. And minus 12 divided by 0.5, this is minus 6, obviously, right? So that's minus 6. Then you would have a line with the slope 18 goes 0.4, okay? So that brings you to 1.2. So the slope would be slightly larger and, up to here, let's say. Sorry. Yeah. So that is now 1.2. And then eventually it comes to, with the slope minus 2, it comes to 0 eventually. So this is now your shear, this is your moment diagram. So we did all this because we wanted to compute the maximum moment in order to insert it in this formula. Now from this picture, it's very clear. The maximum moment, or the absolute value of maximum moment, it happens here. So it's 6. So all you have to do is to come back here and just put moment as being 6 kilonewton meter. So to finish this, we just remember that M max, or let's say the magnitude of it, is 6 kilonewton meter. And from that, you can calculate D to be 0.07413, which, again, we we would basically overestimate it to have a safer design. That's 75 millimeters. So the question asks you for the diameter near to the nearest millimeter, right? So we need to kind of make it, we need to truncate it, but we truncate it in a fashion that it is safe. So we overestimate, we do not underestimate. All right, so this was the second exercise. Do you have any question? Is all good? All right. The third exercise is the following. If the resultant internal moment acting on the cross-section of the picture has the magnitude of 520 Newton meter and is directed as shown, so you have this. Determine the location of y bar of centroid, the bending stress at points A and B, and the orientation of the neutral axis. Now, there is a lot of calculation in this example, but there are a few important points. I don't want to go through those calculations. These are very standard. You need to calculate moment of inertia and so on. But I want to emphasize the little or the subtle points that you may be missing instead of just emphasizing on those. Okay, the first thing is, remember we have this formula when you have this combined bending problem. We had a formula mz times y divided by iz plus my times z divided by iy. Okay, so that was the first formula you need to remember. And when you want to use points A and B, you need to be careful where you choose these coordinates. Okay, so for instance, after you find out your centroid, you should remember that the axis y is upwards. So when you want to calculate, for instance, the distance for point A, here you would have a -2, okay? And then, okay, there's another minus and they cancel each other and so on. That's one thing that you need to be very careful about. The second thing you need to be very careful about is that when we did these sort of examples and introduced our formula, let's say y equals, we had this thing that we said y equals tangent alpha times z, for instance, and that, that tangent alpha itself was something like iz over iy tangent theta. Okay, and tangent theta was basically the angle that you had between these two moments, my and mz. All right? So in that sort of example, we chose this convention. So this was our angle theta, okay? And based on that, you would calculate your angle alpha. Okay, so this was important that you had your coordinate y here and z here. Now that in this example, your moment is given in this particular direction, your theta would be this angle, okay? Or if you want to be, write it as a negative or as a minus angle, it would be this. Okay, so you should be careful that theta in this example is also negative itself. Or it's more than 90 degrees, depending on how you want to write it down. Okay, so you need to pay attention to that. And then when you calculate alpha, the same holds for alpha. Okay, so alpha also would be a negative angle. So it would be, let's say, eventually, this would be your coordinates, and this is your angle alpha. Or again, if you want to do it from this side, this will be your angle alpha. Okay, so that's that. All right, so I'm going to just write down, let's say, the important pieces of this puzzle and the solutions for you, but I think these are the points that you should have been careful about. Okay, so in order to proceed with this example, obviously you need to calculate mz and my. So from the, let's say from the picture, from the components, you can see mz is minus 480 Newton meter, and my is 200 Newton meter. Again, pay attention, there is a minus here because of the particular direction. So that enters here. That's that. Then you need to calculate the, let's say, y bar for your centroid. Okay, so centroid is here. We calculate y bar from this upper line. Okay, so you start from this, and you want to find this distance. That would be what we call y bar. Okay, so you know how to calculate that. Basically, the formula is simple. It's just sum of y bar for each of the parts, each section divided by sum of the sections. Okay, and if you do that, you will find y bar to be 0.0574 meter. Okay, then based on that, you calculate Iz and Iy also. Again, for Iz, you do, let's say, Iz for each section plus that offset term. And if you do that, let me just write it. Actually, so this would be something like sum of Iz for each part plus, let's say, area for each part times, distance for each part. And if you do that, you get Iz to be 57.6 times 10 minus 6 meter to the power 4. You do the same thing for Iy. And that would be 0. Well, let me just write it like we did before. It would be 366.8 times 10 minus 6 meter to the power 4. And now, based on that, you can have everything you wanted here. So for these formulas, now you have the quantities you wanted. You can just use them and calculate the stress at points A and B as the question asks you to do. So sigma A would be then, again, using the formula that we had up there, sigma A becomes minus 1.2, well, minus 1.3 megapascal, and sigma B will be 0.5, well, 0.6 megapascal maybe. Okay. This is, let me just make it clear, 5.9 megapascal. Okay, and then you eventually use that formula for the angle alpha. Okay, so you would say tangent alpha is Iz divided by Iy times tangent theta. And as I said, the trick here is to pay attention that theta itself, you can write it as a negative angle or minus, 62. This is in degrees. And if you use the formula now, for alpha, you get minus 3.72 degrees. Okay? Or again, if equivalently, you can think of it as, I don't know, 176.28. Okay, so that would be your alpha. Okay, so this is the answer to this question. As I mentioned, there are a few subtle points, but the rest is just calculations. If you take those points correctly, I think you should be fine. Is that clear? All right, so the last exercise actually is pretty simple. It's very standard. But this is the topic we haven't covered yet. We will talk about it on Monday. But the important thing here for you is that it's a shear problem. And for shear problem, we will learn there is this formula VQ over IT. And if you want this tau to be max, so the shear stress, if you want it maximum, you are looking for a point that your Q is maximum, and basically your your thickness is minimum. So that point would be somewhere here. And again, we will do a very, very similar example in the class. And also you have some in your homeworks. But if you do that, you get tau equals 5.19 megapascal. It's a very standard problem. And then again, I is simply, moment of inertia. You would calculate it and you get something like this. Okay, and also Q max. We will talk about what Q max is, but this would be 8.65 times 10 to minus 4. Q is just that area moment that we talked about previously. All right? So this is the fourth exercise, as I mentioned. We didn't talk yet about this shear problem. We talk about it in the next lecture. So that was everything for this recitation today.